work, and absolutely delighted to welcome and introduce one of my colleagues, Dr. Andrew Timmis, who is a senior lecturer in transport and planning. So been a very valuable member of this network in terms of bringing those two environments together. His talk is going to look at the use and challenges of applying life cycle assessment methodology to indoor assessment, and considering the interaction between objective impacts on air quality and the kind of subjective considerations we might bear in mind in terms of thermal comfort. So a real nice bringing together of the urban environment to the internal environment, which we all rely on for work, for rest, and for play. So I'm now going to hand over to Andrew, and look forward to your presentation, Andrew. Thank you.
Thank you very much, Malcolm. Let me just share my screen. Let's share that one. Just go in presentation mode. Can you confirm that you're able just to see?
Yes. Yeah.
Very much. Well, thank you very much, everyone, for kind of giving up some of your lunchtime today to kind of explore this issue of including indoor air quality within life cycle assessment methodology. And thank you, Malcolm, for those kind words of introduction. As Malcolm said, I'm Dr. Andrew Timmis, Senior Lecturer in Transport and Planning. And part of my kind of research background has been looking at the application of life cycle assessment methodology in various different aspects of kind of product development. So going all the way right from a 787 Dreamliner aircraft, right the way down to applying life cycle assessment for the suspension spring of a Jaguar Land Rover vehicle. But what I'm going to be exploring today is actually how can we apply life cycle assessment methodology when we're thinking about kind of building design. But why do we need to start thinking about integrating indoor air quality dimensions into the life cycle assessment methodology process? So for some audience members today, and whether you're watching kind of the recording later, I'll give you an introduction to life cycle assessment methodology. For some of you, it may be new or kind of something that you've heard or read about tangentially in your work. I'll talk about the application of life cycle assessment to a whole building design, and then explore the rationale for including indoor air quality in life cycle assessment. But it's by kind of exploring that inclusion of indoor air quality, it throws up lots of challenges in terms of actually how current life cycle assessment methodology is constructed. And then start to explore some approaches for the future. And I'm hoping actually this presentation today might actually throw up some questions and discussion that we can have towards the end of this session. So moving on to the next. So firstly, it's that question about what is life cycle assessment? So life cycle assessment is in itself a quantitative environmental assessment technique. So by applying a life cycle assessment methodology, what we're trying to do is try and quantify all of the different environmental impacts that would result through either the manufacture of a product, the delivery of a service, or the running of a system. So if we're thinking about a whole building, it actually cuts across lots of those different aspects. The purpose of a life cycle assessment is to try and support decision making. So we can start to understand what the environmental impacts are that are occurring as a result of decisions which are being made. We can start to try and then identify maybe hotspots within the supply chain of that product or service of where environmental impacts are occurring, or particular environmental impacts are occurring as a result. And what we're trying to do by applying a life cycle assessment methodology is explore the environmental impacts that occur right through the life cycle of a product. So that's going right from described in field as its cradle, so right at the beginning, so from raw material extraction, energy production, then transforming those raw materials into products which we might be using. So from a building perspective, it could be steel, it could be cement, it could be a HVAC system if we're thinking from an air quality perspective, transport, construction, and then all of the environmental impacts that occur throughout the use of that product, service, or in this case, a building. And then ultimately going to the grave. So actually at the end of that product's design life, at the end of a building service life, what happens to the environmental impacts occurring from demolition? And what we're looking at really is this flow of energy and material throughout a product's life cycle. So going into and out of the environment, where are those environmental impacts occurring? What is the nature of those environmental impacts? What's the size of those environmental impacts? So LCA methodology is relatively well established. There is an ISO standard, series of ISO standards to follow if you're thinking about applying a life cycle assessment methodology to any particular type of product, service, or system. So starting off with that goal and scope definition, what's the purpose of the assessment that you're undertaking? What are the boundaries that you will be drawing around it? And we'll explore some of this as we go through some applications when we're thinking about indoor air quality and buildings later. Once you've obviously started to define the scope and the boundary of your assessment, the next stage is to construct what's called the inventory analysis. So this is trying to identify the material, energy, and water flows throughout that product's life cycle. So we're identifying the inputs and quantifying them, but also starting to identify and try and quantify the outputs. So if we're thinking quite simply, for a building, for example, during its use phase, one of the things that that building will be doing will be consuming electricity. So that would be one of our energy inputs into the system. But actually, we need to start thinking about, well, actually, how is that electricity produced? Is it from coal? Is it from gas? And then what would be the environmental impacts which would occur as a result of that electricity consumption? Draw from databases about kind of the amount of CO2 that could be produced, the amount of NOx that could be produced, SOx, water consumption, land consumption in the provision of that input into that product life cycle. Once we've built up this database or this inventory of inputs and outputs throughout this product's life cycle, we can then start to try and identify what the impact would be from that. So it's taking that inventory data, which is that quantification of material and energy flow, and then turning it into what the environmental impacts across different environmental indicators would be. So most typical life cycle assessments start to try and identify environmental impacts across 10 to 12 different indicators. And the reason why there's some variability is start to think about actually what's the goal of that life cycle assessment, or if there's environmental impacts which are particularly pertinent to a particular product, or maybe some indicators which aren't particularly relevant in that assessment. So notable ones, if we're thinking about doing a life cycle assessment on a building, especially when we're thinking about indoor air quality, we could be thinking about its contribution to global warming potential, human toxicity potential, respiratory organics, respiratory inorganics. And then each life cycle assessment will identify what indicators they're reporting against. So starting off just quite simply, and I know this is not kind of anything to do with indoor air quality or a building at this stage, but we can start to use a life cycle assessment to start to try and answer questions such as this. So if we imagine we have two bottles, the functional unit in this case is we're trying to provide someone with 500 milliliters of water, which of these two products is better for the environment? And actually applying the life cycle assessment in this instance would allow us to try and answer quantitatively what that answer should be to this question. So hopefully it's a product that we're all familiar with, 500 milliliter bottle of PET plastic water bottle, and then a reusable aluminium bottle. So if we think about that term, or which is better for the environment, if we take each of those two products, and undertake the life cycle assessment to try and quantify the environmental impact that could occur through its production. The aluminium water bottle is going to produce 100 times the climate change impact of a plastic bottle. But obviously, your aluminium water bottle is reusable and you can reuse it many times over. So we obviously make some assumptions about how that aluminium water bottle will be used. So let's imagine it's used 3 times a day. So you're consuming 1.5 litres of water throughout the day. And we think about what the typical life cycle of that water bottle would be, so probably about 2.5 years. But actually, over the life cycle of that water bottle, actually the aluminium water bottle would have 1/30th, so about 3% of the global warming impact, as compared to if you were using a single-use plastic bottle each time that you were drinking. So it's starting to understand actually where do the environmental impacts arise. So in this case, very much in the production phase, but the use phase of this aluminium water bottle actually saves the environmental impacts compared to the counterfactual. So we can start to try and use this when we're thinking about actually how do we design a building, technology do we want to integrate, what materials do we want to use, how would that building be used over its life cycle, to try and understand design decisions to try and identify which is better for the environment. So applying life cycle assessments in buildings is kind of a growing trend, starting to try and understand more holistically about the environmental impacts which can occur through the built environment and construction. So these are just kind of ASHRAE positions, which many of you might be familiar with. So by 2030, trying to halve greenhouse gas emissions arising from the built environment, trying to reduce embodied carbon within new construction by at least 40%. And then that long-term goal fitting in with kind of the global net zero strategy. By 2050, all new and existing assets must be net zero greenhouse gas emissions across the whole life cycle. So we're not just thinking about the construction phase, we're also thinking about a building which might have a design life, a service life, 20, 40, 60 years. Actually, how do we ensure net zero greenhouse gas emissions over that entire life cycle? So that we've got many challenges. Carbon emissions and greenhouse gas emissions are just one environmental impact. And we've potentially got other competing demands on how we want our buildings to be designed and operated. Some of them can be explicitly linked to greenhouse gas emissions and environmental impacts of energy consumption, as an example. But we also need to think about what other competing demands might we have for that design of that building. Are we designing for thermal comfort? Are we designing to reduce pathogen exposure, which is obviously topical with COVID? Are we trying to improve indoor air quality? Are we trying to enhance the user experience or make a building adaptable for users' needs and preferences? How do we ensure that that building is adaptable over the course of its design or service life? How do we ensure that the capital cost and operational cost is acceptable? So life cycle assessment can help us start to think about how do we try and tackle these competing demands. So are we ensuring that we're not moving one environmental impact, say carbon emissions or greenhouse gases, from burden shifting from one environmental impact to another? So by improving the carbon efficiency of the building, are we making the indoor air quality worse? Or are we making thermal comfort worse? Or are we reducing the adaptability of that building in the future? And the majority of building scale life cycle assessment studies neglect indoor air quality. And as I'll demonstrate over the next couple of slides, there's no reason why indoor air quality can't be integrated within a traditional or standard life cycle assessment methodology. And the issue is, if we ignore indoor air quality and it's overlooked in the application of life cycle assessment, are we designing products, in this case buildings or processes, which are optimized at the expense of building occupants? So are we designing buildings which actually might be exposing their occupants, users, to enhanced risks or exposure to poor indoor air quality, and then all of the negative health consequences which may well arise? So we try and develop, well, what does a life cycle assessment framework for buildings look like? So a traditional life cycle assessment very much focuses on those external impacts which might be arising as a result of construction. So we can be looking at other environmental impacts, so non-human health impacts, trying to quantify the global warming impact, contribution to acidification, eutrophication, ozone depletion, ecotoxicity. And we can also try and start to quantify the external human health impacts which might be arising as a result of emissions to the atmosphere. So emissions of NOx, emissions of SOx, or carcinogens into either aquatic environments, soil, more generally. So that's what a traditional life cycle assessment categories would try and integrate. But if we start to think about internal impacts, well, we can start to identify what the human health chemical impacts could be. So we can reasonably predict potentially what local indoor air quality could be if we're thinking about quantities of particulate matter, quantities of volatile organic compounds. So we can start to think about, if you go back, remember that life cycle assessment is thinking about mass flows and energy flows throughout a life cycle. We can actually start to think about, well, we can quantify the internal impacts through that use phase because we can understand that mass flow throughout the system. And many of these human health impacts, whether they be external or internal, are quite similar. External ones are relatively well understood. There are databases of what the effects of those emissions could be. And therefore, we could use that potentially as the basis to try and start to understand what internal air quality impacts could be over the life cycle of that building. So what we're trying to understand is try and characterize those indoor air pollutants and the effects that they may have. So within life cycle assessment methodology, when we're trying to understand an environmental impact, especially around toxicity, it's the use of this use-tox system. So use-tox is a unified system for evaluating substances in environment and toxicity. Allows us to try and start to understand, well, what can the impact be of chemical exposure on human health? So what we're trying to understand is actually what's the ultimate fate of that pollutant once it's been chemical, once it's been emitted. What's the exposure pathway? So how long are people being exposed to it? Is it through direct inhalation? Is it through dermal absorption? And actually, ultimately, how toxic is that particular chemical we're being exposed to? So what we're trying to identify through the use of use-tox is actually development of this characterization factor, which is made up of the intake factor, or the intake fraction, which is what's the quantity of a pollutant which is being intook or inhaled as a proportion of that which is being emitted. And then starting to understand what's called the effect factor. So actually, what's the long-term health consequence of the consumption of that particular pollutant? So this is what we do through what we've been thinking about external emissions, and there's no reason why the same process cannot be followed for understanding indoor air quality impacts. So what we're trying to understand, if we just have a look at the diagram on the left-hand side to begin with, is this exchange and flow of chemicals and pollutants throughout different environments. So it could be we start kind of at the global scale, which is the largest square, kind of emissions to air or emissions into agricultural soil, natural soil, aquatic systems. There is obviously then a relationship transfer between kind of continental scale and global scale. And again, we could be thinking at a more limited environmental scale. And then we could be going to, and this is where I suppose the breathing city element comes into, kind of the urban air scale, where we have that interaction and flow of pollutants between continent, urban environment, and also the outdoor urban environment into the indoor. And then we can go down into the kind of the smaller spatial scale, which we're thinking about is that indoor air and the transfer of chemicals between, in this case, kind of general circulation within the air and intake into, as we're interested in this case, into humans. So whether that be through absorption, through deposition on surfaces, and we need to start thinking about actually what's the circulation of that air, how long are people being exposed. So we need to try and start to think about that intake factor. So actually how much are people being exposed to, what quantities of people being exposed to. And this is going to be dependent on several different variables. So actually what's the pollutant that we're talking about? You know, is it particulate matter? Is it VOCs? Is it formaldehyde? What's the overall ventilation rate of the building or the room? How long are people being exposed to that particular pollutant? Is that pollutant degrading over time? What's the number of people being exposed? So if we think about that intake factor at the very extreme, you know, we might have very poor indoor air quality with a very high concentration of particulate matter and volatile organic compounds. But if no one is being exposed to it, is it actually a problem? Whereas we might have a lower level of particulate matter, volatile organic compounds, but a large quantity of people being exposed to it. So therefore, the intake factor would be greater. Other key variables which are going to be of interest: what's the volume of the building? How is pollutant mixing throughout the building? And obviously, these are going to be variable on a building to building basis. And as we know, building regulations, building codes across different regions of the world and countries are very different. So we get to a situation where each building may well be unique when we're starting to think about actually what's the intake factor of these pollutants. So one of the things that we need to start to think about is actually how can we model indoor air quality and integrate it to be able to then understand what the characterization factors are. We might be able to simplify this through following such as this decision tree, which I've kind of adapted from Helveg. You know, do we have one or few point sources of a particular pollutant? If the answer is yes, you know, is the room small? Yes, then maybe we could have a very simplified one box model. If it's not small and we've got kind of well mixed conditions, then maybe still a one box model would be appropriate. How close are people being exposed? Are they very close? Yes, then maybe we might be able to have to develop a more complex model. So it's starting to think about, well, actually, how do we start to characterize and understand the indoor air quality in that particular location to then identify what's the most appropriate way of understanding and modeling that indoor air quality. But we know that buildings are not necessarily static, and we might also have indoor environmental conditions which can also have a negative health impact. So we might all be looking at kind of non-chemical impacts, allergens, pathogens, what the building conditions are in terms of stress and mood disorders, which we know as the evidence is growing that can have negative health consequence if we're thinking about the mechanisms causing poor health. And then we could also start to think about, well, actually, we might be looking at non-health impacts. So we could be thinking about what might be effectively on productivity and performance as a result of ventilation, different lighting conditions, etc. So whereas previously we had kind of a relatively well-developed method of using kind of the use tox methodology to start to try and understand and develop characterization factors for indoor air quality pollutants, here we've got a basket of impacts where we don't have necessarily the same quantity or quality of databases to draw from. So actually starting to have to try and identify empirical parametric relationships to understand the impacts which may well arise. But the question also becomes that actually a life cycle assessment is very good when all of the conditions of a product are static. So for example, I can environmentally admonish myself after this if I'm drinking from a disposable plastic bottle, which I know is very bad for the environment as a result of life cycle assessment. But the conditions of the production of this bottle are probably relatively static. Whereas the use phase of buildings, which are going to be a significant period of time, are dynamic. So we could be talking about the conditions of a building changing throughout the day. It could be changing on an annual basis throughout seasons, where we might have input heating, cooling during the summer period, heating during the winter period. And we also might have dynamic conditions over that life cycle of the building. Maybe the use of the building changes, the occupancy of the building changes, technology changes, or we integrate new sources of local air pollutants in that particular location. So this is just an example of just trying to capture some of this dynamism from Colling et al. 2013. So if, for example, oops, lights go out. If we just start with the bars, looking at estimated occupancy, the occupancy of that building changes over the course of the day. And therefore, if we're thinking about the characterization of any particular pollutant, the intake factor is going to change throughout the day because we've got more people exposed to it. On the top, for example, the line with the square markers showing outdoor particulate matter, PM2.5, varies throughout the day as kind of urban conditions change. And if we look towards the bottom of the graph, where we've got the line with the crosses through, this is showing kind of what the filtered PM2.5 looks like, the profile of it, and with the circles, the red, the indoor PM2.5 also varies throughout the day and actually maps onto some of the relationships and trends that we see in the outdoor PM2.5. So we need to think about, well, actually, our buildings themselves are dynamic as we go through the day, and therefore simplifying buildings into having static conditions is not maybe necessarily going to capture fully the environmental impacts which could occur throughout the life cycle of that building. So therefore, when we're starting to construct a life cycle assessment and going through that inventory analysis, starting to try and quantify the environmental impacts, we need to start to think about this dynamicness in the data and exposures and how we can start to try and estimate the variation in them. And also that occupant needs may differ either throughout the day, seasonally, or throughout the life cycle of that building. Or even actually individual occupants may have different requirements of the building. So different temperatures, which is going to have obviously have different impacts if we're thinking about ventilation, heating. So there's a move to try and develop what are called kind of dynamic life cycle assessments, which start to try and capture these system changes. So rather than having a kind of static life cycle inventory of mass and energy flows throughout a building's life cycle, we might have to develop dynamic life cycle inventories where we can start to capture some of this variation amongst environmental impacts. So this could be through development of scenario building or analysis, what if scenarios, Monte Carlo analysis, to try and capture the full range of variation that we might see in different categories. Also, enhanced emphasis on sensitivity testing. What are our key variables of interest, and what might the effect be of changing some of the assumptions or capturing some of the variance that we might see if we're looking at kind of measured inputs into a building. But also thinking about those feedback loops and system thinking, if you were to make a change in one aspect of the building design, what might the impact be on the rest of the system, and therefore the environmental impacts occurring as a result. So lastly, just to kind of focus a bit on some of the challenges that we're thinking about kind of integration of indoor air quality in life cycle assessment. So we can separate them really into kind of what are general building scale life cycle assessment issues. So constructing a life cycle assessment for a building is very data intensive. Probably primarily because each building may well be unique. The quantity of materials being used, the particular design, its use may differ, how that building is being operated and the operational conditions, which may well affect the energy consumption throughout that 40, 50-year design life of the building. And this is obviously going to be a particular issue if you're trying to undertake a life cycle assessment of a retrofit to an existing building. So actually, is there the availability of data specific to that case? And what are you going to be dependent on drawing case studies, drawing on assumptions? So there's an opportunity looking ahead, kind of BIM, digital twins of new buildings, whether we can start to kind of automate some of this life cycle assessment using the digital models that we have been developing. Building and lifespan of service life may not be reliable. So are some buildings going to be operated for less than their design or service life, others longer? And also uncertainty in how those buildings are going to be operated and the operational conditions. So we're thinking ahead towards 2040, 2050, with some of the expected impacts of climate change, particularly if we're in an urban environment where we might see more extremes in terms of average temperature increases or more extreme temperature events, which may have a greater demand for energy consumption if we're thinking about HVAC systems, as an example. And then we've also got some challenges of actually how do we integrate the indoor air quality aspect into life cycle assessment. Because indoor air quality conditions are dynamic, it will therefore affect the characterization factors which we typically use for a life cycle assessment. Obviously going to be variation as a result of occupancy or building use change. So therefore, one element that we need to start to work on is actually how do we develop the evidence base to develop new characterization factors for indoor air quality in a variety of different settings. And equally, how do we develop specific indoor air quality models for a particular building? That we're thinking about circulation of a particular pollutant around that building. And also some uncertainty in the effect factors. So we may have a particular pollutant, we may have a set of kind of environmental conditions within the building where there is growing evidence around health impacts, but uncertainty in actually the mechanisms between exposure to a particular environmental impact, pollutant condition, and actually what the long-term health impacts can be. So a need for greater research on actually making some of those data points more robust. So that kind of draws to a close for my presentation. We'll have some time for questions in a moment. But just as a summary, so life cycle assessment is a useful decision support tool to try and develop holistic understandings of environmental impacts. And that can be equally applicable to kind of a product, such as the water bottles that we started through, right the way through to kind of something like building scale, of trying to understand all of the environmental impacts which may well arise as a result of the production of that building. Indoor air quality is often not included in building scale life cycle assessments, but we know that the use phase of a building is sometimes its most significant source of environmental impact. And therefore, where we have a use phase, could, as I say, for 30, 40, even longer years, actually starting to understand the environmental impacts, the internal environmental impacts, and indoor air quality are going to be particularly important. Indoor air quality at present has all the characteristics suitable for inclusion in an LCA methodology. We can identify the emissions, we know the pollutants, growing understanding of how kind of they're mixed and people are exposed to them, and therefore we can develop the characterization factors to include indoor air quality as an explicit output of life cycle assessment. But the key thing is that building conditions and this indoor air quality is dynamic, and therefore we need to try and think about how do we capture those changeable conditions within a life cycle assessment. So thank you very much for your attention and input, and welcome any questions. So I'll stop